We've already seen a side angle side theorem for two congruent triangles. This one's a little relaxed a little bit, and it's just the side angle side for similarity. So given a triangle ABC and then triangle DEF, just try to draw it either smaller or bigger, doesn't matter. But make it exactly the same shape. I did my best here to make this triangle the same shape as this one, meaning the angles are all the same. The internal angles, angle B and the angle F are congruent, and so on. So given these two triangles, if the ratio, the fraction, AB, that length, over this corresponding side, which is DF, if that ratio, that fraction, is the same as the ratio as this side, AC, over, let's see, AB should be with, oh, I think I messed these up. I did. Let me see if this fixes it. That should fix it. I labeled them in the wrong order. The correspondence, A goes with D, B goes with E, and C goes with F. So now we're right. So if AB over this length is the same as AC over this length, the way I'm going to write that is this length is some number K times AC. And this one is K times, that would be AB. Sorry about that, a little messy. K times AB, this will be K times AC. And what is that number K? This is the constant of proportionality, this ratio. That's where K would come from. So in this case, when these two sides are in the same proportion, we don't have to say anything about the third side if the angle in between those two sides, these two corresponding angles are congruent. So angle A is congruent to angle D. So what we have is side, angle, side. Now these sides are not, the corresponding sides are not congruent once again, but they're in the same proportion. Okay, you have side, angle, side. In this case, you have two similar triangles. Once again, we've said this before, if the constant of proportionality K were 1, then we would have two congruent triangles. But in this case, we just have two similar triangles. And in fact, that also means, well, we'll get to this number 8. If this is true, this diagram is pictured correctly, then what do you think the length of this side is going to be? It's going to be K times the length of BC. And we'll get to that, I believe, in number 8. This is called side-side-side similarity. And just to remind you, the side-side-side theorem for congruence of triangles just says that if the three corresponding sides are congruent to the three corresponding sides of the other triangle, then you have two congruent triangles. What we're going to say here for number 8 is slightly different. We've got our two triangles, ABC and DEF. We have to say that if AB over DE, similar to what we had up here, is equal to BC over EF is equal to CA over FD. I want to make sure I did this correctly. We've got AB over DE, correct? Then we've got the second and third, BC over EF. And then we take the third and the first, CA over FD. Yes, this is the correct correspondence. If all of those are equal, then we have two similar triangles. And once again, any one of these would be considered the constant of proportionality K, this fraction. So a real simple example. You can do this however you'd like, but two triangles with side lengths 3, 7, 8. For the first one, all you have to do is multiply them by any positive number. And I'll choose, maybe I'll take k equals 4. So 3 times 4 is 12. 7 times 4 is 28. 8 times 4 is 32. You could have picked any number. You could have doubled them, 6, 14, 16. Two triangles that have these side lengths are similar to each other. Moving on to number 9. Given B and D are, let's see, okay, good. I didn't call this triangle. It shouldn't be A, B, C. It needs to be A, C, E. Let's make that B and E, like that. So given that B and D are the midpoints of these two sides, so AC needs to have B right in the middle there. And then D is the midpoint of CE. Okay, so we've got two midpoints of two sides. And we're saying that prove, given A, B, and BD are the midpoints respectively, prove that we have two similar triangles where ACE is the big one. And let's see, it's not going to be BCD. Yeah, it is going to be BCD. ACE is the big one, and then connect those two. We've got BCD as the second triangle, the smaller triangle. So again, we obtained the smaller triangle by just drawing the line segment connecting two midpoints of the sides. All right, well, the proof will be pretty easy. Notice that both of the triangles share this angle C. So we'll start off by saying that, let's see. I guess I need to say that. Maybe I don't need to say that. Maybe I'll write it up here. Angle C is congruent to angle C. That's the reflexive law. Maybe I'll do it. Let's see. Sorry about that. Looks like I already have a reflexive law here. So I'll say that the angle C is congruent to angle C. The first one is going to be the definition of the midpoint. That is going to say that BC, this length, is 1/2 of AC. That's the definition of a midpoint. And then there's a second one that goes along with that, that DC is equal to 1/2 of EC. Again, both of those are by definition of the midpoint. And then, because of this, we see that this is 1/2 of the bigger side. This is 1/2 of the bigger side. So our constant of proportionality is 1/2. And the angle in between them is congruent in both of the triangles. So by SAS similarity above, the very top, we know that those two triangles are similar. Triangle ACE is similar to, not congruent, triangle BCD. Again, just to remind us, it's this side over this side is equal to the length of this side over the length of that side, and the angle connecting them is the angle in the middle is congruent in both triangles, obviously. Okay, so that's an example and proof. And let's look at the last one in this video, number 10. Okay, number 10. Draw an isosceles triangle ABC. Well, I drew one over here. And let's say A is the top and then B and C on the left and right at the bottom. This is the base. So these would be the two sides that are congruent, making it an isosceles triangle. Okay, so AB is equal to AC as we've shown here. Now, the measure of angle BAC, that's 28. All right, so let's label M on BC as the, let's see, angle. Let's label M on BC so that AM is perpendicular to BC. Okay, so that just means drop a perpendicular down to the base. By definition, we can say since we're dropping a perpendicular, we know that's a 90-degree angle. Label N on AC so that, let's see, that would be M. That's the midpoint. Label N on this side. Where do we want to put it? We want MN to be perpendicular to AC. So it's like dropping another perpendicular from here to there. So now we have another right angle right there. And we would call that point N. Find the measure of angle CMN. CMN. So we're trying to find the measure of that angle right there. Okay, drawing a picture wheel, we already did that. First, we want to show that there are two triangles in this picture that are congruent. Okay, neither one of them is the big ABC. We're going to show that ACM is similar, not congruent. If I said congruent, I meant similar. Is similar to MCN. Now we know they have at least one, we have this angle in common. They both use angle C. Okay, well, we'll use angle-angle similarity, which means we need to find two angles that are congruent to each other. All right, we have angle C is congruent to angle C. That's by the reflexive property. Every geometric object is equivalent to itself. So that angle, maybe put 3 of them there. This angle is congruent to itself. Then angle MNC is congruent, MNC, that's this guy, which we know is a right angle, is congruent to AMC. Well, that's a right angle. Yeah, two right angles are congruent, so both are right angles. So all right angles are congruent to each other. And now we have those triangles, MNC, AMC. They are similar to each other by AA similarity. They have two angles that are congruent to each other. So those two triangles are similar. So for the last step, we need to say that the measure of angle CMN is equal to the measure of angle CAM. Well, we know that because of, well, yeah, I haven't used this expression yet, but corresponding angles to similar figures are congruent. If you have two similar triangles, which we have here, the angles are congruent. And that's what this means. Corresponding angles of similar figures are congruent. Okay, and what is, let's see, what's that going to be? Well, corresponding parts of, okay, we've got, actually, and given, we could say this is 14. Why is that? Well, they add up to 28. This angle and this angle add up to 28. They are corresponding, we have two similar triangles. So this angle is the same as that. Let's see, we dropped the perpendicular. CMN, CAM, CAM. Hope I didn't skip a step. It turns out that this triangle, AMC, is congruent to AMB as well, because the base angles of isosceles triangles are congruent. I may have left that line out, but that's why we know that if these two angles are equal and they add up to 28, they're equal to 14. So that gives us the measure of CMN and CAM being 14. And that's what we were trying to find.